Good evening, guys. It's 8:55, it's a Tuesday night, and it's a good time to do some physics as per usual. I hope you're excited. Tonight I'll be answering questions 21 and 22 of the 2017 HSC paper, following on from my previous videos of answering the multiple choice questions. If you guys are enjoying this series, could you please like, share and subscribe to the playlist or just the videos? And if you've got anything that you'd like to see that I'm not doing, please just leave a comment in the comment section below. So, question 21 I'll start with. A laser emits light of wavelength 550 nanometers. Calculate the frequency of this light. So, first equation we need for this one is C equals F lambda. And this says that the speed of light, C, is equal to the frequency of that light multiplied by the wavelength. So the question is asking, calculate the frequency. So that means that is going to be the subject of our equation. We have C, which is always 3 times 10 to the 8 meters per second. You can find that in your formula sheet. And we have the wavelength equals 550 nanometers. 1 nanometer equals 1 times 10 to the minus 9 meters. So it's 1 billionth of a meter. So we can say 550 nanometers equals 550 times 10 to the minus 9 meters, or 5.5 times 10 to the minus 7 meters. So they're just the numbers we need to use. The first thing I'm going to do is I'm going to rearrange my equation now. So C equals frequency times wavelength. If I want to find frequency, I'm going to divide both sides by the wavelength. And that means I get C over lambda equals F. And then I just plug in my numbers, so I get F, I'll draw it right over here, F equals 3 times 10 to the 8 meters per second divided by 5.5 times 10 to the minus 7, and that gives me an answer of 5.45 times 10 to the 14 hertz. Cool. Okay, question B. The electrons in a metal must absorb a minimum of 5 times 10 to the minus 19 joules in order to be ejected from its surface. Pardon me. Explain why electrons will not be ejected from this metal when photons of wavelength 550 nanometers strike its surface. Support your answer with relevant calculations. So the thing to remember about this is that when we have electrons being liberated from the surface of a metal, this is the photoelectric effect. And this only happens, or one of the situations when this happens, is when the atoms of that metal, if they absorb the photon, then the electron is released because of the energy that's absorbed. Now, a certain minimum amount of energy has to be absorbed in order to break the bond between the metal and its electron. And if that energy isn't there, then that photon doesn't get absorbed and it just does something else. So, for this question, what we need to calculate is the energy of the photon that comes from, or the energy of the photon that's meant to try and liberate this electron. So that's what we're going to test now. So we know that the minimum energy, E min, equals 5 times 10 to the minus 19 joules, which I get from here. Now I need to calculate the energy of our electron and see how it compares to that. If it's less than that energy, then the electron won't be liberated. Oh, it's not going to be liberated, because I have to explain why it's not. Okay, so E equals HF is the formula we need to use. And that says the energy of a photon is equal to Planck's constant H multiplied by the frequency of that photon, measured in hertz. And this will give an energy in joules. So H, which we can find in the Planck's constant, is 6.626 times 10 to the minus 34 joule seconds. We already know the frequency is 5.45 times 10 to the 14 hertz. And now we just need to calculate the energy, so we just sub in our numbers, and we get E equals 6.626 times 10 to the minus 34 times 5.45 times 10 to the 14. And that gives us, if I put that in the calculator, I get 3.61 joules. Oh wait. 3.61, didn't find that properly. 6.626 times 10 to the minus 34 times 5.45 times 10 to the 14 equals 3.61 times 10 to the minus 19 joules. So that's obviously less than 5 times 10 to the minus 19, so we can say the electron will not be liberated. So the electron will not be liberated because the photon does not have enough energy. And that should be enough for that question. And guys, when we're answering HSC questions, something we want to pay attention to is how many marks the question is worth. So this one is a 3-mark question, and it asks a few things. It says, explain why the electrons will not be ejected. So explain. And support our answer with relevant calculations. So I'm assuming that the bulk of the marks, at least 2 of those marks, probably, are going to be from that calculation, because it's a decent calculation. And then we support our answer with a very short statement, and that should be enough to get us the full 3 marks. So that's an important analysis, guys, when you're answering HSC questions. What is this question asking of me, and what do I need to answer it fully to get the full marks for the question? Okay. Question 22. A torque is applied to a nut using a wrench as shown. So torque is just another way of looking at force applied from a distance. If we had an infinitely long wrench, we could say that that nut would be really infinitely easy to turn. But if we had an infinitely short wrench, then it would be infinitely harder to turn. It'd be like trying to turn the nut with your hands, which is obviously much harder. Now, torque is given by the formula, or torque is the product of force and distance. So the higher the force, the higher the torque. So if I'll say, if force goes up, torque goes up, write a tau, torque goes up, and if distance is increased, distance from the center or distance from the rotation point is increased, torque also increases. So this question is asking, suggest 2 ways that the applied torque could be increased. So obviously, if you push harder on the wrench, you will increase the torque. And also, if you increase the distance from the center at which you hold the wrench, so if you hold the wrench as far back as possible, you will also increase the torque that you can use. So the way I will write that is torque can be increased by applying a larger force or, don't need that comma, force, can't spell anymore, force, or applying the force further from the center of rotation. And you don't have to use my exact words, guys. Anything to that effect would be pretty good. Okay, I'm just double checking. That's a 2-mark question. We've suggested 2 ways that the applied torque could be increased. I think we've answered that question fully. Question B. A coil consisting of 15 turns is placed in a uniform 0.2 Tesla magnetic field between two magnets. A current of 7.0 amperes flows in the direction shown. Calculate the magnitude and direction of the torque produced by the side BC of the 15-turn coil. Okay, so this question is asking us to find the torque, and it's going to ask us, or what it wants us to do is use the torque formula we just used in question A. So if torque equals force times distance, and we need to figure out the torque on side BC, so this side, we just need to calculate the force on side BC and the distance from which it applies. Okay. So also the side BC is going. We can work that out pretty quickly using the right hand rule. If we look at our magnetic field, it's going from north to south, so it's going this way. Our current is coming down. So if I apply my right hand rule, so an arrow going this way, and I do some fiddling with my hand, I can see that BC is going into the page. And I'll attempt to draw that like this. Hopefully that's obvious, but whatever. So we say BC is going into the page. That's the first thing I'll write. BC is going into page. So guys, you don't have to draw that sort of stuff when you're in an exam. I'm just doing it for your benefit, or maybe if you could do it in an exam for your own benefit. Okay, let's calculate the force on the wire. So right now we've got a force on a wire carrying an electric current in a magnetic field, and the formula we use for that is F equals B I L sine theta. Okay, we're given the numbers. B equals 0.2 Tesla, I equals 7.0 amps, and L is, which is the length of side BC, is 0.08 meters, and theta is the angle between the current and the magnetic field. Because the magnetic field is going across the page and the current is going down the page, we can say that the angle between them is 90 degrees, because they're at right angles to each other, and so, which makes our life easy, because sine of 90 degrees equals 1, which means anything we multiply by becomes just that number, because it's just 1. So we get F is now just 0.2 times 7 times 0.08, and then you can write times 1 if you want to, but you don't really need to write that. Okay, and if we plug that all into the calculator, we get an answer of 1.68 newtons. Now, that's the force applied on BC. We need to remember that the question is asking us to calculate the torque. Okay, so the torque is that force applied from a distance, and we can say that it's applied from a distance from the center line of that coil. So the coil has a width of 0.06 meters, which means the distance between BC and the center is just half of that. So we can say that the torque is equal to 1.68 times 0.03 meters, and that gives us an answer of 0.05 Newton meters. Cool. And so guys, that's how you answer questions 21 and 22 of the 2017 HSC paper. If you guys found this useful, please like, share and subscribe. If you have any comments, please leave them in the comment section below. And if you've got any advice on how I can do this better, or how it would better meet your needs, that would also be great. So I'm doing this for you guys. Please let me know. Have a great night, guys, and continue doing physics to your best ability.